Okay, here we want to look at a linear system. Okay, and one thing that we discussed earlier, we said that when we're solving linear equations, three things can happen. You can have a unique solution. Okay, that's where we would have to say x is equal to 4, y is equal to 3, z is equal to -6, all right? Or x is equal to 0, y is equal to 5, whatever that may be. We can have no solution. Okay, that's the case where no matter what we put in for x and y, we will not satisfy this system. Okay, but one thing I want to look at now is what happens when we have infinitely many solutions. That's what we're looking at in this place. So the first thing I want us to do, let's look at this system. We have x plus 2y minus z is equal to 3. 2x, 2x plus 3y plus z is equal to 1. We want to solve this system. So the first thing we want to do, of course, is write the augmented matrix. Okay, so now once we draw our augmented matrix, we still have the same goal to get row echelon form. All right, and in this case, we won't have that many steps to get row echelon form. So the first thing we want to do, we want to multiply -2 times row 1 plus row 2 to give us a new row 2. A -2 row 1 plus row 2, and that's going to give us a new row 2. All right. So now, once we solve this equation, once we solve this problem, we'll have 1, 2, -1, 3, remember? And now that's going to be 0, -1, 3, and 5. Now, this is row echelon form. But the first thing we should start noticing is that we have more variables than we have rows. And we should just see that this looks funny. We have X, Y, and Z, but in this case, we only have 2 rows. So the only way that we would solve this is to introduce the free variable Z is equal to T. I'm going to say this again. Introduce the free variable Z is equal to T. What this is called is obtaining the parametric form. Okay, we have more variables than we have rows. So now we still want to back substitute. So we're going to have -y plus 3z is equal to -5. But as we said, z is equal to t. All right. So in the end, after we solve for y, yeah, I'm going to move y to the right side and this -5 to the left side. We end up having 5 plus 3t is equal to y. All right. Now, since we've used back substitution, we want to continue and we want to go forward. Let's look at our top equation. That's going to be x plus 2y minus z is equal to 3. We know that z is equal to t, so let's move right here. We want x plus 2. Remember, yeah, I'm going to put 3t plus 5. If you put 5 plus 3t, it is the same thing. Minus t is equal to 3. And I'm just going to go step by step so we can actually see this. After we distribute, x plus 6t plus 10 minus t is equal to 3. x plus 5t plus 10 is equal to 3. And once we solve this and get x by itself, we're going to have x is equal to -7 minus 5t. So our solution is going to be -7 minus 5t, 5 plus 3t, and t. All right. This is parametric form. Our solution is in parametric form. And basically what this means, hypothetically, just say we said z is equal to 0. That means y would be equal to 5, x would be equal to -7. That's going to work. Just say t is equal to 1. That means y would be equal to 8, and x would be equal to -12. That would still work. So no matter what we put in for t, it's going to work as long as it goes into this form. This is a case where a system has infinitely many solutions. And infinitely many solutions. All right, we just want to make sure we knew exactly how it looked. Okay, so once again, we have a unique solution, no solution, infinitely many solutions. And the other times that we get parametric form are usually when we have homogeneous systems. So we can look that up as well. All right.